So we know that magnetic field and magnetic field lines are related to vector, means they have direction and magnitude. Remember vector? So they have direction plus magnitude. So the question is, what we are trying to answer over here is that what is the shape and direction of magnetic field that is produced by a straight wire? So before we answer this question, I want to make sure that we understand that and we are sure of that. There is a magnetic field that is produced by flow of charges. Okay, that is flow of, actually it's not current, should be charges produced by a current. So instead of flow of current, it is produced by a current. Okay, if not flow of charges. So we need to be sure of that because maybe it was something else that rotated that copper wire. You know, so we want to be sure that okay, this is the cause. Current is the cause of the wire being rotated. Okay, so to be sure of that, we have something called as Orsted experiment. I'm not sure of the pronunciation. So the experiment, what do you think we'll make use of? One is we need the current. So current, we see current in quite a few places, but one which we can control and which is very easy to use is using a battery and a set of wire, right? Maybe a resistor, just in case, variable resistor. That is, we can change the resistance. Obviously, a switch, and we have the wire, and we have the complete circuit. If I switch on, there is flow of charges. But how can we check if there is current flowing through it? With the help of an ammeter, just in case. And how much current and all of that, we can help make use of ammeter. Okay, now we can be sure of the current is flowing. Now, how can we be sure that it produces a magnetic field? See, we can't just look at it and tell, okay, there is magnetic field around it. Something should be there to help us figure it out. So can we use some ferromagnetic material, right? Maybe if I keep a iron nail or something like that, maybe it might get attracted and we'll get to know. But to be frank, that's not practical. We don't see iron rails running around in our house, even though there is a lot of wire running around, right? So what else can we use? Well, the most easiest and convenient thing will be a compass, is it not? Compass can detect even the slightest change in magnetic field. That's the idea of a compass, is it not? So it's quite easy to get as well. So maybe you can keep it around or above or below a wire, right? So this makes sense. So if I would have done it, I would have done with all of this. Let's see what Orsted experiment does. So the experiment is about this. This is the aim. We saw that apparatus, long straight copper wire. Okay, makes sense. Battery, plug-in key, compass. In my case, ammeter as well. Right? Makes sense. And the wire and everything is connected like the one which we discussed. Right? It is convenient. And yeah, they place the compass around the wire, actually above if not below. That also makes sense and convenient. But we are looking at two different cases. This I didn't discuss. One is to connect the battery in such a way that you have the current flowing in clockwise, and here it is anti-clockwise. So I just flip the battery. So one thing that I'm written over here is in the experiment which I'm going to show, I have not flipped the ammeter. Okay, so you can see here positive is connected to positive over here. Here positive is connected to negative. So not flip the ammeter. Please remember that. So one small thing, I've not done the exact setup. I have ammeter, battery, and all of it, but I have not made use of copper wire as a single wire. What I've done is this is kind of an antenna, not kind of an antenna. It acts like an antenna. It has a lot of copper wire running around it. So basically, all of it put together we can feel that, or we can think or imagine that there's a big fat wire running over here. And this is a convenient place for me to keep a compass. So, I've made use of it, right? So this is the setup that I'm going to use. Everything else remains the same, just that instead of a single straight wire, I have an antenna kind of structure that I'm going to use. Okay, so let's have a look at the procedure, and then let's do what the procedure tells. Connect the circuit as per the diagram 1, insert the key, note down the deflection in the compass. Makes sense? Connect the circuit as per the diagram in case 2, plug in the key, note down the deflection in the compass. So one more thing is, you should look at the deflection initially as well. That is one more thing. If I had thought of it and typed it properly, one more point I would like to add is, note down the initial deflection, right? Not deflection per se, but initially where the compass is pointing towards. Initial position, yeah, that's better. Initial position of needle in compass. Okay. So one thing that also is important, because if you don't know the initial thing, then how will you find any deflection? So it's common sense, but yeah, I want you guys to be sure that you need to observe it. I want you guys to be observing initially as well. And once I switch on the current, read the deflection or check the deflection, and also read the ammeter. Have a look at all of it. So basically, in my video that you're going to watch, so you'll have an ammeter. So we'll have this setup. So next to that, I have an ammeter. Okay, so have a reading of that as well. Right, when I switch on, there will be some reading, positive, negative readings over here. That also we observe and check the deflection. So I've made the video slow, but if you guys want to pause and have a look at it properly, please do that as well. But yeah, please observe, because the deflection is not that big, right? Because the voltage and the current and the setup is kind of small, so you won't see that big deflection. Okay, so I would like you guys to pause the video and watch the experiment slowly throughout. It's not that big, or it's not that confusing. It's more set of observation, but please see to that you make the observation properly. So now pause the video. So what is that we observed? The compass deflects to the left of the wire in case 1, and it deflects to the right of the wire in case 2. So it basically deflected when we had the current switched on. That is one more thing, right? When there was no current, the needle always pointed to the initial position. When we switch on the current, it's when we saw the deflection. Okay, when we switch the current, the direction of the needle switched, indicating, this made sure that current is the cause of deflection. Double conclusion, or double check. So we did a double check, and yes, current is the cause of the deflection. So let's see the conclusion. Wire carrying current produces magnetic field. The direction of the deflection of the needle is reversed if the direction of the current in the wire is also reversed. So this is an extra point that we can make a note of, right? Okay, so this is called as your Orsted experiment. So quite easy setup, quite simple procedure, and important observation and conclusion. So the next big question is, how does the magnetic field look like? Okay, magnetic field line produced by a wire look like. That's the next thing that we're going to see. So now you guys have to, yes, this is part of your syllabus. So you guys have to note down, other than, of course, this part. Everything else you guys have to note down. And please pause the video, note it down.